Hello everyone, it is my great honor to introduce our research. We propose a novel event-driven learning algorithm for temporal-coded spiking neuron networks. We begin by giving the motivation of our study. We must recognize the success of deep learning is based on huge energy consumption. In contrast, brain-inspired spiking neural networks, SNNs, process information in discrete spike. So, they provide an energy-efficient alternative to deep learning. Time to first spike, TTFS, is one of the coding schemes in SNNs. It encodes information by the single spike time, further reducing the energy consumption. However, despite the energy efficiency of TTFS-based SNNs, their application is limited by the lack of effective training algorithms. Current training algorithms for TTFS-based SNNs face two challenges. First is the oversparsity of spikes, which is due to three aspects: firing mechanism, asynchronous transmission, and TTFS-based decision strategy. According to the firing mechanism, spiking neurons transmit information only when their membrane potential reaches the threshold, and the sub-threshold information is discarded. In addition, as shown in Figure B, the input spike of gray input neuron is invalid for output neuron. So, the asynchronous transmission of SNNs further reduces the active neurons number. Furthermore, after learning, the spike time of output neuron is advanced, making more input neurons become invalid. Another challenge is the complexity of finding the causal set. This process involves many sorting and iteration, resulting in massive training resources and increased latency. To tackle these problems, we propose a dynamic firing threshold, which regulates the spiking activity of each layer within a time window. We integrate the proposed DFT into rel-PSP neurons. It utilizes a linear spike response kernel. Based on the membrane potential and the proposed DFT, we can directly calculate the output spike time. Overall, the output can be divided into three classes: premature spikes, spikes within time window, and no spike emitted. Based on the DFT, we further propose the DTA-TTFS algorithm. The left figure shows its forward propagation. It makes the network with layer-dependent firing feature, and the spike time windows of each layer do not overlap. These two characteristics effectively solve the previously mentioned challenges. To drive the gradient backpropagation, we need to calculate the output spike time with respect to input spike time and synaptic weight. This can be easily obtained from the DFT-based neuron model. We begin our experiments by comparing the proposed method with other related works. Results demonstrate that our algorithm achieve the best performance, and also achieve a harmonious balance between accuracy and sparsity. Furthermore, we conduct validation experiments. In the left figure, we prove the proposed DFT can provide SNN with the layer-dependent firing feature, and the spike time windows of each layer do not overlap. In the right figure, we prove the DFT can effectively solve the oversparsity of spikes. Finally, we demonstrate the energy efficiency of our algorithm through theoretical analysis and neuromorphic simulator, namely CANMore. Both results prove the energy efficiency of our method. That's all. Thanks for your watching.